Good morning, everyone. And today I would like to talk uh, about my thesis with you. And I'm happy to like join the meetings and looking forward for presentation of other participants. And I appreciate your effort to connect people from different fields, at least to yeah. Um, I wanted to talk with you about feedback in autocatalysis and how the inherent positive feedback of autocatalytic accumulation of a product can be harnessed out of equilibrium to perform some let's say, intelligent functions of chemical systems. And like intelligent is very strange word, not often used for describing physical or chemical systems because we don't really feel them alive or conscious. But yeah, we may try to define the intelligence for reaction networks as a ability to integrate incoming chemical signals, change its internal structure according to it, so make a decision, and then adapt to this input, and then maybe in the form of memory reflect previous experiences of the system, and so on. But we will be there shortly. The adaptation, this would be actually amazing if we had chemical systems that would allow for real chemical adaptation, and we could create them from bottom to top. From simple components. And I was thinking about what is adaptation like in living nature. And I understood, and I would like to discuss it with you. It's very important for me that the adaptation is always connected to some form of feedback in a system. And like on this slide, we have the trivial examples of a heat control in a house on the left, when you have a negative feedback. So the controller punishes the system stops the heating when the temperature is reached. When outside is getting colder, the punishment um, arrives later. So the room can be the yeah. This like the whole system, the heater plus the controller allow for their temperature in the room to adapt to external conditions. And the positive feedback example is kind of weird because imagine that you have a loudspeaker and a microphone and you kind of move them towards each other. Then you get this extreme noise, terrible one. But then you try to drag it, then you try to separate them, but you will still have a lot of this noise coming out because it self-amplifies a lot. So this noise will be persistent until you really separate them quite far. Even if in the beginning at this distance there was no massive self-amplification. And like trying to describe what is feedback a bit more formal, I don't know, it's something that connects outputs of the system to its inputs. So it kind of feeds the stuff back. And I like this example a lot. Yeah, when we have this trivial, like very trivial mathematical structure with feedback, we can get a lot of different behaviors, even if the mathematical expression is very, at least it looks very simple. And I was trying to find in chemistry examples of like chemists studying feedback. And surprisingly, I found stuff, and I understood that some of Nobel Prizes were uh, given for research of the feedback. And strikingly, a lot of contemporary technologies on which our society rely a lot come from this understanding of the feedback. Like, and the most straightforward thing is PCR. Like when we need to, for example, I don't know, do anything with DNA, we need to amplify it, and this would be a cycle of a feedback. And biochemists has done an amazing job of to really harness this thing to optimize not only like structure but also reactions and so it's very important. I just want you to get a feeling that the study of chemical feedback is not something that comes from the abstract ideas. It really can contribute to our society, but we unfortunately never know how. And the first, the most obvious question is how to create feedback relations in a chemical system if we construct it like from simple components. And it's not a full list, it's not a classification, but just to understand what can happen if you have the product that inhibits the reaction itself. If you have a reagent that in high concentration does not allow for reaction to occur fast, or if you have a competition, or if you have autocatalysis, and this is very interesting. So then you have a feedback, and like my thesis was about like how you can incorporate the autocatalysis as the feedback element in your chemical system, and what can you gain out of it. But it's not the whole story, because for such a chemical system that would do something continuously, that would respond, that would be able to get input, give output, and also maintain its internal structure and change its internal structure, it just has to be out of equilibrium. And the way of elevating the stuff from equilibration we choose was the flow conditions. So on this image, I need to take a pointer. Yeah, this image, you see the pumps, you see the reactors, you see the tubes go from pumps to reactors, and you see kind of the digital control elements here to allow for interaction with the system. Like here we put the input, and here we read the output. In my case, was most of the time just absorbance detection. And the input in this case is the pressure in a given syringe. So you just increase the flow rate of one component, decrease the flow rate of another component. So there are buffering components, so you can always have the same flow rate, but then you can manipulate the concentrations of guys coming into a reactor. And in chemistry, it's not a surprise that if you have a nonlinear reaction in flow setup, you get a lot of weird things. And even such a simple reaction as depicted here, see like 3 steps, just like so few equations, but you get very sophisticated behavior of the system if like you analyze this mathematically. And I would talk about 2 reactions today. So one is an enzymatic one, the degradation of trypsinogen down to trypsin, which is autocatalytic. And another one is the chloride toluene reaction, which is extremely fast and will be important for different types of reactors. You see here 2 different types of reactors. So those ones, they are just the tanks with a styrofoam inside. So we assume that there is a perfect homogeneous mixing inside, and everything is nice. But here we premix everything in a passive mixer, and then it comes into this tube and something interesting is happening. And I was I have constructed the system like that we have the autocatalytic core. It's like normal autocatalytic reaction. A plus B leads to 2B, and B again participates in this step. It's the inhibitor that does not allow for the autocatalytic species to play its role. And there is an activator that enhances the rate of this reaction. So let's say there are 3 modules in this system. So the one is the autocatalytic core that constantly tries to amplify itself, the inhibitor that tries to shut it down, and the activator that can increase the rate, let's say increase the strength of the positive feedback. Kind of the positive feedback becomes stronger, so the reward like at a given time of autocatalytic development will be higher. And starting from the this case, when we have the autocatalytic core and inhibitor, see this is again the schematic depiction of our setup. So we have different syringes with stock solutions of compounds. We have the PC that allows us to control the thing, and we have a sequence of reactors that allow for the detection, online detection. So it was actually amazing that we can immediately see what happens in the reactor and immediately see how the system relaxates after perturbation and so on. We started from just showing that there is some form of bistability in our system and flow. So we have this reaction, and for those who are not into enzymes, the trypsinogen is just, you see this small leg is just one small leg longer than trypsin. So when this piece is cut, trypsinogen becomes trypsin. And the protein that binds to trypsin so tight that trypsin can't act as a catalyst anymore. We checked like what happens if we this on x-axis here, it's initial concentration of inhibitor. We checked like what happens if we change concentration of input concentration of inhibitor from a low amount to high amount and from high amount to low amount. And if we initially have very high concentration of this inhibitor, then like on y-axis, it's the output concentration of trypsin. We have no output whatsoever, and then we move lower, nothing changes. Then we move lower, it's sudden increase of the trypsin concentration. But on the other hand, if you start from very low concentration of inhibitor and we gradually increase it, then we kind of can't get anymore to this state where the output of trypsin is fully suppressed. And this difference, yeah, we could call it bistability, but to be correct, it's not exactly like that, because in this system, one state is stable, another one is unstable. So I'll get into it a bit later. And we had control over the pump, so why not to try to perturb the system with cycles of inhibition. So here on those on these two figures, you see how inhibitor concentration goes up and down. We call this inhibition sweeps, and the blue line is the concentration of trypsin in the outflow of the reactor. And you can see that like unlike the linear systems that would try to respond without dragging memory from one cycle to another, that do not have this drive of self-amplification. But again, it's not the only condition. Competition and other things could also allow for the feedback. So we have, for example, this situation. So we cycle, and the output suddenly just explodes, and then the system actually is not really sensitive to this. And here it's sensitive when the concentration of trypsin is outcoming trypsin is quite low, so we kind of see that it tries to repeat this input pattern. But when it's already exploded, let's say, it's not sensitive anymore. It's in this upper branch state where we kind of struggle to shut down the catalytic activity of trypsin. And it resembles me a lot the long-term potentiation in neurons, you know, like when you have the stimulus that excites the neuron so much that it can't stop firing, whatever input you continue to give to it. So it starts to look like something not intelligent maybe, but something that has internal structure that allows to make not maybe decisions, yeah, but to be in different states and kind of choose between them according to rates of reactions and according to input physical conditions. In another case, we have amplification between cycles. So we feed it with all the components, and we give inhibition sweeps, and we see that from first to second to the third one, the amplification of signal is happening. And we try to kind of classify and investigate it also numerically using the simple mathematical model that describes this reaction quite well. And we saw that there are different modes of interaction of our inhibitory sweep inputs with the dynamics of this feedback. We claim this. We claim in this paper that we actually do signal processing there on the manner of some old school analog devices, and yeah, happens only due to the internal feedback. Moving further, yeah, I've noticed that there are some ions that that affect the reaction rate of this conversion a lot. And I checked it in batch. How did it look? So I picked 3 ions: calcium, lanthanum, and neodymium, and with calcium, the accumulation of the autocatalytic product is quite slow, let's say. And if we change the ion, we have a dramatic increase in overall velocity. But not only this, we also get different dependence of the reaction rate on the concentration of the activator. Of course, for calcium, it just looks like a saturation at the given concentration of trypsinogen and trypsin in the beginning, as well as for lanthanum. But for neodymium, it's different. So I propose some scheme that explains this, that allows to model that, and this is the key instrument here that adds another like additional nonlinearity out of the initial component concentration this system. And if we check what's going on in flow, so here on this experiment, the upper part is the input, and the black line is the concentration of this neodymium, the one which is nonlinear, just going like up, 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 up. And this line without dots or dashes here is the profile of the output. And yeah, we see that there is some optimal concentration of neodymium where the output is high. And there are concentrations above this optimum that does not allow for trypsin to be produced. There are concentrations below this optimum. And if we add simultaneously several ions, for example, we add calcium to neodymium, we can manipulate the shape of this curve. And yeah, if we add lanthanum, we kind of move the development of autocatalysis earlier in concentration of neodymium. If we add calcium, we kind of shift it a bit later. And by this, we constructed the ability for this autocatalytic cycle to understand like simple, let's say, mathematical structures, because we can modulate quite sophisticated profile of the outflow using several instruments. And it was quite clear how to force the system to become a Boolean logic machine with a memory. Because if you have a nonlinearly acting activator, then you can find such inputs of this activator that when they combined, there is no trypsin activity in the outflow, or it's a high trypsin activity in outflow. And imagine that we have the XOR gate, the one which is quite hard to demonstrate in chemistry typically due to its nonlinearity. But the system does it, but not due to autocatalysis. Like if we have input 0, 0 in face of, we have two syringes of neodymium, and if both of them are not pumping, then the input is 0, 0. If only one of them is supplying the reactor, we have high output. And if both of them are active, we again get low output. That's how we build XOR gate. And any other gates can be built like that. But because the system is autocatalytic, we can still switch between the stable and unstable state. So it's a system that has a decision mechanics inside, but it also remembers this decision. And this experiment is illustrating that quite well, I believe, because we were talking on previous slides about this part of the system, this subsystem that allowed us to drag some information from like one impulse to another impulse, to have some kind of memory and hysteresis. When we add an activator, then the interplay is quite beautiful, because imagine that we just start from low inhibitor and optimal concentration of the activator. The output explodes, everything is nice, but then we increase the concentration of inhibitor, and the output kind of drops down, but not completely. And then we give not optimal concentration of activator when the activity is down, and everything goes down. And then we release this stimulus of the activator, but we don't release the stimulus from this thing, from the inhibitor, and the system doesn't recover at a given time. But then we kind of restart everything. We remove this influence. It gets back. We do the same stuff, but now it recovers, because now the concentration of an inhibitor is not enough to keep it in this unstable state where no reaction is occurring. And this is amazing. This is the major result of this paper. I like it a lot. I'm not sure if you kind of get that, but I love it. Then I was thinking that I would want to try the faster reaction that would allow me to have something more sophisticated. And this is a well-known reaction between chloride and tetrathianate. It's known to be very nonlinear and fast. And when it's, you see here, when it happens in batch, so this is a very small scale experiment. When it happens in batch, we just have autocatalytic front that converts all the reagents into the products. But if we put it, if we move it away from equilibrium and pump solution of this reaction through the tubular reactor, then we start to get quite weird behavior, because this experiment shows what happens if we just cycle between a bit higher and a bit lower concentration of autocatalytic ion inside, because this reaction, this autocatalysis is driven by H+. So H+ is the product, H+ is the catalyst, and we just using the pumps, we just inputting a bit more H+, a bit less H+, a bit more, and we have like those cycles. And we see that normally, if it was a reaction without dramatic self-amplification, we would just have this blue color that corresponds to reagents. We would just have it traveling till the ends of the reactor. But it's not that straightforward now. Now the reagents can't reach the ends of the reaction of the tube, and it was very interesting. And probably it happens due to so-called Poisson flow, when you have the in laminar flow, when you have the kind of core part of the flow that does not experience shear forces on the walls from the walls of the reactor, you can have slightly faster movement of liquid in the core. And we see it like when we trace the segments of a channel in time. We see that like in the middle here, we when we try to displace the product with the reagent, we clearly see that the core of the flow has this blue line. So inside the solution of product that almost immediately converts reagents into itself, we have a tiny thin phase of reagent that gets eaten all constantly by the product. And in case we displace the reagent with the product, this transition happens almost immediately, because you just need a very small portion of autoactivator to convert all the reagents into autocatalytic product. And here it's not possible, because there is a balance between the rate of washing out everything from reactor and the rate of the reaction. And the shorter the residence time, harder the system for the system to convert itself to the final state. And playing on this difference, we can really control how far the phase of the reagents may go down the tube. And so here we vary input concentration of sulfuric acid a bit. It's just like 1 millimolar difference at constant concentration of other reagents. And then we build so-called chemographs. So you just imagine that we have those snapshots, a lot of them, and we slice them, and then we try to see how the middle line of this image looks in time. And we see that there are triangles of this like reagent phase, and we see different angles. So the sharper angle is like the faster reaction is, and there are quite interesting dependencies of shapes of those triangles on the schema graphs on initial conditions and like insertions of components. And it allows us again to do similar stuff, to threshold input frequencies of acidic perturbation, for example, like here. So if we increase the frequency of cycling between bigger and smaller and bigger amounts of incoming acid inside this reactor, we can find a point where the reagent mixture can get down the line fully, can exit the reactor. But if we just increase the frequency of our cycling a bit, it stops kind of reaching the end. And because it's spatial, we can have several angles of looking at this, and we can also interpret those results as the pulse width modulation, because we have the incoming pulses of acidity, and if we take different points on the of this tubular reactor, we have these pulses. We have kind of an echo going from the like earlier points of the reactor to later points, and we can modulate the, so in the output our signal can be transformed like that. And in electronics there are circuits that do it, and they also rely on the feedback. And for me, it was very interesting to try to reconstruct it with the chemical reaction. Making it a bit more sophisticated, we can use not just the autocatalytic reaction, but the autocatalytic reaction with other constraints. So we could try BZ, and I love this experiment because it's very beautiful. You have this this line established, and I believe that a bit more sophisticated signal processing can go with a more sophisticated reaction. And I do really think that it's a promising tool, maybe for some yeah, for real applications actually. But it's not the whole story about this interplay between your flow regime and the rate of your autocatalytic reaction, because then we can bend the geometry of this tube. For example, we can create several pockets without altering the total volume of the reactor, and we get the dramatic effect because here the turbulence appears. You just can't simply wash out the stuff out of this pocket, and the autocatalytic reaction here tends to develop and redevelop and redevelop, and you simply can't wash out the products from the small pockets, and the result, like how far the reagent portion can move through the tube, changes dramatically. If we take some different but also planar geometry, like here, so we have obstacles, we have triangle, we have this planar layer and triangle obstacles, and we try to find some stationary state there. We observe truly strange things. So just check this out. I would never expect that that I would really see in such an experiment regions where the turbulent flow dominates and regions where the laminar flow dominates, because I cycle between two concentrations of acid on input, and this is a stationary state. You really have you have two phases. One phase is the reagents, one phase is the products, and they have a very thin border, and it just stands there. when you don't change the flow rate. This was amazing, and it led me to like idea of like, why don't I create a maze for the liquid? Why don't I check if yes?
Just a second. The maze here, or the white triangles, is
Yeah.
extrinsic or develops in course of the reaction. And
It's
this is a given.
It's a PDMS made reactor.
Oh, so
And
this is a given structure imposed.
yes.
Thank you.
So it's a design.
Yeah, it's a design. Yeah. It
Yeah.
doesn't happen as part of the reaction. Thank you.
Sure, yeah. The reason behind this design is
Sure, yes,
to
it does not.
no.
Okay, thank you.
The reason behind this design is to force the regions where clearly the flow would be turbulent, because behind the triangle it will be turbulent. And when it's turbulent, then your product just stays there. It can't leave. And when we have more sophisticated geometries, we can see that at some seemingly random point. So here we were increasing in time concentration of acid slowly. Like at some point, at some almost random point, you have the autocatalytic development, like above the threshold, everything starts to going on, and you have very sharp borders, like between areas where you have the phase of reagents and areas where you have a phase of products. And this is very surprising for me. And yeah, we can interpret this thing as a maze navigation by this like swarm of the portions of the reagent. Or we can tell about the kind of hidden computation done by this chemical reaction to visualize the laminar and turbulent areas. Yeah, so it's also about the intelligence, let's say, of this thing, but it's very subtle. So we can't say that it really solves math problems and goes to school, and but yeah, I'm thinking about the analogy between classic circuits from electronics and those chemical reactions. I found like really perfect example of Schmidt-Trigger. The same reaction with activator, but now the leading activator is not the weird one, not the one which is at high concentration inhibits everything. It's a lantern. So this is the patch experiment. Where we increase the concentration of lantern, we see that the rate of autocatalytic reaction increases a lot. So we have a grip on the strength of positive feedback. Same as in Schmidt-Trigger, it's this resistor. If we increase resistance, the feedback there becomes stronger. Or we can vary it, so we can transform the incoming voltage differently into output. And this system acts exactly the same. And I have calculated how the stability changes. But this was actually the last slide, huh? Yeah. I understand that it's very it's hard to, because I was thinking about this stuff and I was writing about this and I was doing it, and I would say that's esoteric a bit. So I would